Welcome to the next video in the Real Analysis video series, and in this video I am going to give my solution to just the first two because the video gets really long. The second one takes some time, or maybe the third one, in any case. So I'll only show the solution to the first two of these problems, and in the next video we'll do the last two. So, okay, let's get into it. The solution for the first problem, showing that if x is a subset of y, then sup x at least, or sorry, at most. Notice that, if we simply prove that sup y is one of the upper bounds of x, then the result follows, because after all, sup x is the least of the upper bounds, and therefore we just need to know that this is an upper bound, and then it becomes automatically greater than or equal to. So we just show that sup y is an upper bound on x. Okay, but we know that sup y is an upper bound on y. It is very easy, and I think I basically show that here. It is very easy to show that any upper bound of x is an upper bound of y because of the subset relation. And therefore, we get the result immediately. I think that really is all I need to say here. So Halmos. Okay, here I spotted a mistake in the proof that I initially planned to present, so I'm going to present the proof differently this time. So first of all, show that that inf of negative x exists. Right? Because this problem is all about doing something with inf of negative x. We know sup of x exists because we know that it is non-empty bounded above. So as we've already seen, the sup must exist. But we don't know that the inf of negative x exists. Well, it is very easy. It's very easy to show that if alpha is any upper bound of x, then negative alpha is a lower bound of negative x. So I leave that as an exercise. It's very easy, so you should go ahead and do it. But from this, we can very easily demonstrate that negative x is non-empty and bounded below, therefore its infimum must exist. Now, even that principle that a set which is non-empty and bounded below must have an infimum, does not follow immediately from the things that I have proved in these videos. But if you follow the same basic steps, we did a proof that the sup, the least upper bound property, so it should be very easy to prove the corresponding lower bound property. Although now that I think about it, that is in fact one of the assigned, right? Like, is that not? Yeah, I guess that is actually the one of the problems that I set out next, but it should be easy to do here. So I guess actually, in retrospect, part of what you have to do here is proving one of those dual theorems for the duals between the sups and the infs, but it shouldn't be hard, I don't think. So I leave that as an exercise to the viewer. And once we have it, we know that the inf of negative x exists, and then we can start reasoning about it. So, okay. From there, once we know that inf negative x exists, next need to show that the sup of x is negative inf negative. First of all, we have to show that this thing is an upper bound of x, and then show that it is the least of all the upper bounds of x. So let's start with the first, showing that negative inf negative x is an upper bound of x. To that end, let little x be an element of big X, and we're trying to show, right, so maybe we would say want to show that this little x is less than or equal to negative inf negative x. So that's the goal. How do we get there? Well, I guess somehow we need, if we're starting from here, we need to somehow introduce negative big X in some relevant, interesting way. So let's maybe talk about negative little x, which must be an element of negative big X by definition. And then we know that the infimum of negative big X is a lower bound, so we must have that inf of negative big X, which we know to exist, is now less than or equal to negative little x, and then negative inf of negative x is greater than or equal to x by multiplying by -1, and we get exactly the thing that we had hoped to get. So there it is. That shows that -inf negative x is an upper bound on the set x. Okay, 2. Let's show that it is the least of all of the upper bounds, and to that end, let's consider any other upper bound. And again, it might be nice to see explicitly what we are trying to show. We're trying to show that -inf negative x is less than or equal to beta. Now, certainly we're gonna have to use this property that beta is an upper bound of x, I think, basically based on a thing that I've already mentioned close to the start of this video. We know that negative beta is a lower bound of, let's say this is a lower bound of negative x, as we've said earlier, and I left as an exercise, but then this must mean that because the inf is the greatest of all of the lower bounds, then we get negative beta is less than or equal to inf of negative x, multiply throughout by -1, get beta is greater than or equal to -inf negative x. And that is exactly what we wanted to prove. So there is the HALMOS. And so that is 2 problems, right? That is the end of the second proof, I believe, right? So yeah, so that's the end of the proof of the second part, and we'll pick this back up in the next video.